All right, here we go. This is my second ever calculus video filmed this way, and I am already starting to love this experience. I think this is going to be really good for kids and for teachers, especially as we prepare for the fall semester exam next week. So let's look at this question. It says, consider the curve given by the equation y cubed minus xy equals 2. And then they go on to say it can be shown that dy dx equals y divided by 3y squared minus x. So this is just a fact. They're telling us this. And even though the question does not ask us to, I want to do a little side work here. I want to actually show anybody who's watching this at home, where did that derivative come from? A problem like this one here is called an implicitly defined curve. Implicitly defined curve. Implicitly defined because we have the x's and the y's mixed in together on the same side. When you're finding the derivative of an implicitly defined curve, well, here's how it works. The derivative of y cubed will be 3y squared, but since y depends on x, y is a function of x, it's 3y squared times the derivative of y with respect to x. Minus, now we need to take the derivative of xy. And because this xy is being multiplied together, this is a product rule question. Product rule tells us to take the derivative of the first term, which is 1, leave the second one alone, plus now we leave the first term alone, times the derivative of the second, which is dy dx. Equals, continue taking the derivative of 2 is going to be 0. Great, you've successfully found the derivative of an implicitly defined curve. In order to solve this for dy dx, well, I have dy dx showing up over here, and I have dy dx showing up over here. What we need is a little bit of algebraic trickery. I'm going to first rewrite this expression, 3y squared times dy dx, minus distribute this through, minus y, minus x times dy dx, that's equal to 0. Because I have the dy dx showing up in two terms, I'm going to collect the terms that involve dy dx on one side. Terms that don't have the dy dx, namely this negative y, get moved to the other side. It was a negative y over here. We added y to both sides. And now we're going to factor out the dy dx to give us dy dx times 3y squared minus x is equal to y. And therefore dy dx is equal to y divided by 3y squared minus x. Now there was absolutely no need for us to do that work because we were told in the original problem that dy dx is equal to y divided by 3y squared minus x. But I wanted to take a minute or two to just go through this process of how we find the derivative of an implicitly defined curve. Okay, now let's get back to the actual problem we're supposed to solve. In part A, we're told to write an equation for the line tangent to the curve at the point -1, 1. Equation of the tangent line, you need a point and you need the slope. When you write your final answer, you'll write it in the form L of x equals m times x minus x1 plus y1. Where does the slope come from? The slope is the derivative. Specifically, we need the derivative at the point -1, 1. So x is equal to -1, y is equal to 1. We have our derivative expression. Everywhere there's a y, replace it with 1. So 1 divided by 3 times 1 squared minus -1. Simplify that carefully. 1 squared is 1 times 3 is 3. 3 minus a -1 is 4. That 1/4 represents the slope. Coming up with that slope gives you 1 point. To write the equation of the tangent line, we're going to write L of x is equal to my slope times the coordinates for the point are -1, 1. So x minus -1, which means x plus 1, plus 1. That's the equation of your tangent line. That earns you the second point. Done and done. No need to do any additional work. That was a 2-point question. And I would say that is a kind question. I would expect most students in an AP Calculus class to be able to correctly solve that without too much panic. All right, now let's look at part B. In part B, we need to find the coordinates for all points on the curve at which the line tangent to the curve at that point is vertical. Vertical. A vertical line has no slope, or the slope is undefined. Well, if the slope is undefined, and we know that the slope expression is this dy dx equals y divided by 3y squared minus x, if this is going to be undefined, well, what needs to happen? Undefined would have to happen when the denominator is equal to 0, 3y squared minus x is equal to 0, but y is not equal to 0. I want to pause on that thought for a second. We've got our derivative expression. Our derivative expression is a fraction. We have the numerator and the denominator. For a fraction to be undefined, the denominator is equal to 0. So we say 3y squared minus x is equal to 0, but that's not the solution. We're looking for points. We're looking for combinations of x and y that satisfy that relationship. Well, the only way I can actually figure this out, I've got one equation and two variables. I need another equation. Where does that other equation come from? That comes from what they told us in the beginning. They told us that all points on this curve satisfy the relationship y cubed minus xy is equal to 2. So I want to do some algebra trickery. I want to think like an Algebra 2 student. I have two different equations. Each of these equations is defined in terms of two variables. And so what I'm going to do is I'm going to rewrite the equation 3y squared minus x is equal to 0 as 3y squared is equal to x. And then I'm going to do a substitution. I'm going to go over to this equation over here, and everywhere I see x, replace that with 3y squared. Well, if I do that, what happens? We get y cubed minus 3y squared times y is equal to 2. Let's do some more algebra. Y cubed minus 3y cubed is equal to 2. Combining like terms, negative 2y cubed is equal to 2. Divide both sides by negative 2. That means that y cubed is negative 1. And if y cubed is equal to negative 1, then y must be equal to negative 1. To get the x value, we're going to use this expression, x equals 3y squared, to say that x is equal to 3 times negative 1 squared. That's positive 3. Finally, we're going to write our answer as a point. We're going to write it as the point 3, negative 1. What's so special about this point is that it is a point on this curve, and it makes the denominator of our derivative equal to 0, which means that it's a point on the curve where the tangent line is vertical. In terms of points being awarded, the first point was awarded when you set the denominator equal to 0. The second point is awarded when you get an equation in terms of one variable that can be solved using algebraic methods. And then finally, when you get the coordinates, the x and the y, for this point. In total, you get 3 points in part B. Not too bad. All right, last one for this video. Let's look at part C. In part C, we want to evaluate d squared y dx squared at the point on the curve where x equals negative 1 and y equals positive 1. Well, d squared y dx squared means the second derivative. That means we want to find the derivative of the first derivative. We were told initially that dy dx is equal to y divided by 3y squared minus x. To find the derivative, to find d squared y dx squared, we're going to have to use the quotient rule again. quotient rule says low d high minus high d low all over low low. What does that really mean? We take the denominator times the derivative of the numerator. And you want to be careful. We're taking the derivative of y with respect to x. So this is 3y squared minus x times dy dx minus high times d low. The derivative of 3y squared minus x will be 6y times dy dx minus 1 all over low, low, the denominator squared. A little bit messy, but not too bad. That's your second derivative, and if you evaluate that, find the derivative correctly, you're going to get 2 points. Now we need to evaluate the second derivative at the point -1, 1. That means everywhere we have an x value, or everywhere we see x, we're going to evaluate at -1. Everywhere we see y, we're going to plug in 1. So 3 times 1 squared minus -1 times dy dx. Well, how are we going to evaluate dy dx at this point -1, 1? Oh, right, we already did that work all the way back here in part A. In part A, if you recall, we determined that dy dx at -1, 1 is equal to 1/4. So, because we're looking at the derivative at the same point, we have all this times 1/4 minus y times 6 times y times 1/4 minus 1 all over 3 times 1 squared minus -1, and all of that is squared. Now, important to know is that a point was awarded if you correctly evaluated the first derivative at the point, and so that would have been getting to this 1/4, and then another point for correctly plugging everything in. There is nothing in this problem that says you have to simplify the answer, so you could leave your answer here and get all the points. If you're going to simplify though, and let's go through and do this, well, let's be careful. 1 squared is 1, times 3 is 3. 3 minus a -1 is 4, times 1/4, minus 1. 6 times 1 times 1/4 is 6/4, minus 1. 3 times 1 squared is 3, minus a -1 is 4, 4 squared. Still a little bit ugly, but we're making progress. 4 times 1/4 is 1, minus 1. 6/4 minus 1 is really 2/4. 2/4 is the same as 1/2. So we have 1 minus a half divided by 4 squared is 16. 1 minus a half is a half. 1/2 divided by 16 is the same as 1/2 times 1 over 16, and we get 1 over 32. Great, that's the correct answer. But here's the thing. If you had made any mistake after this point when you first did the evaluation, maybe you forgot to distribute the negative sign. Maybe you incorrectly squared 4 and said 8. Anything that you do in this area, all that it can do is cost you a point that you just earned. So even though you had the full 4 points back here, if you incorrectly simplify, you just threw away a point that you worked really hard to get. Please don't do that. Anyway, hope you found that helpful, and I look forward to creating more videos over the next few days. Good night.